In this video, we solve problem 77 from section 5.2 of the Larson Calculus text, 10th edition. We're asked to approximate the value of the integral from 2 to 6 of the natural log of x. Now, if we could take the antiderivative, we would just take the antiderivative, plug in 6, plug in 2, and subtract using the fundamental theorem of calculus. But we don't have a technique for finding the antiderivative of natural log of x yet. We will learn that antiderivative technique in Calculus 2 in our Advanced Anti-Differentiation Techniques chapter. But until then, we've got the trapezoidal rule and Simpson's rule for approximating the area under the curve. Now, to make sure that we actually understand what we're doing, we're in Desmos.com where we will visualize the functions that we're using to approximate this function f of x on each subinterval. And then we will show the area under the curve that we're using in the approximation. We'll find that area using the trapezoidal rule formula or Simpson's rule formula. And then we'll look at sort of the error, the upper bounds for the error, and then the actual error in each case. So this is a way of representing the area that we're interested in. The function y equals natural log of x is this purple function. And then I've evaluated the function at x equals 2, 3, 4, 5, and 6 because we're interested in using the trapezoidal rule and Simpson's rule with 4 subintervals. So we're on that interval from 2 to 6. So each subinterval has a width of 1. We've got 5 x values. X naught is 2, x1 is 3, x4 is, or excuse me, x naught is 2, x sub 1 is 3, x sub 2 is 4, x sub 3 is 5, and x sub 4 is 6. So those are our x values, and then the corresponding y values are the natural logs of all of those numbers. So we've plotted those, and this is the area we're trying to find. When we type this integral into Desmos.com, we get that the value of the integral is approximately 5.364. So that's the area under the curve in units squared, provided that we're counting like that unit is the units that we're using in the x direction and the y direction. So we might say, okay, how can I approximate that area under the curve? Well, one way that we can do that is using what's called the trapezoidal rule. Basically, all that we do is on each subinterval that has a width of 1, we create a little trapezoid. We're going to think of those trapezoids as sort of lying on their sides. And then the top of that trapezoid comes from creating a line segment, just like a secant line between adjacent points in our partition. So we're going to go from 2 natural log of 2 to 3 natural log of 3. And we want to draw the secant line there. So the secant line is just the linearization. So rather than calling it y, I'm calling it L sub 1 of y for the linearization on that first line segment. It's going to start at this point and end at this point. The slope is just the change in y over change in x there. So natural log of 3 minus natural log of 2 divided by 3 minus 2. Then we take that slope and we multiply by x minus 2 and add natural log of 2 to get the y values on that line. So we just have a little line segment approximating the function. We do the same thing on the interval from 3 to 4, and then the interval from 4 to 5, and then the interval from 5 to 6. And then we say, okay, if I want to approximate this purple area, the area under the curve, instead of approximating that purple, or to approximate that purple area, I can find the area of each of the trapezoids that are defined by the line segment that connects the x-axis to that function value. We've got the x-axis at x equals 2, and then we've got that function value where x is equal to 2 and the y value is natural log of 2. And then we'll have another line segment starting at the x-axis and extending to that point, and another line segment starting at the x-axis and extending to that point, and so on. So we can do that. And then we'll find the area of each of those trapezoids. So it looks roughly like this. That's the first area. That's our second area. That's our third area. And that's our fourth. So we've got those 4 trapezoids right here. Now, if we want to find the area of a trapezoid, the area of a trapezoid is 1/2 the sum of the bases, base 1 plus base 2, closed quantity, times the height. Now, if we think of those trapezoids as sort of being on their sides, the height is that delta x value, which is 1. And the sum of the bases is the sum of the two function values. For this first trapezoid, base 1 plus base 2 is natural log of 2 plus natural log of 3. So we're taking natural log of 2 plus natural log of 3, that's the sum of the bases, and we multiply by the height, which is 1, and then we multiply by 1/2, and that's the area of our trapezoid. So you do that for the first one, and then you do that for the second one, 1/2, base 1 plus base 2 times height. So we're gonna have 1/2 times 1 times the natural log, or times the quantity, natural log of 3 plus natural log of 4. And then on the next interval, we use natural log of 4, natural log of 5. And the next interval, we use natural log of 5 and natural log of 6. So when we do that, we end up counting that function value, natural log of 3, natural log of 4, natural log of 5, on those interior points twice, because we're using that natural log of 3 value as the second base for the first trapezoid and the first base for the second trapezoid. So we're counting it for two different trapezoids. The only bases that we count only once are the ones at the very end, so that natural log of 2 and the natural log of 6. So that leads to this formula. The trapezoidal rule says the area under the curve is approximately delta x, which is b minus a divided by n. So in our case, that's b minus a is 6 minus 2 divided by 4, because that's our step size. That gives us that 1, times the 1/2, times the sum of all those function values. But remember, we're doubling those function values in the middle, because we're using that natural log of 2 and that natural log of 6 only once for those, the first trapezoid and the fourth trapezoid. But the natural log of 3, natural log of 4, natural log of 5 are used for the second and or first and second trapezoid, or the second and third trapezoid, or the third and fourth trapezoid. So those middle function values are used twice. So we substitute those values into our formula. We have Desmos do the calculation. Oops. And that's what we get. Our area is approximately this 5.33679, approximately. Now, whenever we use a numerical method, it's nice to have an upper bound for the error of the approximation. Turns out that the upper bound for the error of the approximation is b minus a. So in our case, that's 6 minus 2 raised to the third. So that's going to be 4 cubed divided by 12 times n squared. So we have 12 times the number of subintervals squared. So that's going to be 12 times 4 squared times the maximum value of the absolute value of the second derivative on the interval of interest. So what we have to do is we have to compute the first and second derivative. We have to look at its absolute, we have to look at the absolute value of that second derivative on the interval of interest, and then just look for the maximum value of that second derivative on the interval of interest. So it's relatively easy to do. The derivative of natural log of x is 1 over x. The derivative of 1 over x is, well, -1 times x to the -2 power, which can be rewritten as -1 divided by x squared. So that is our second derivative. But we're not interested in the second derivative alone. We need to find the absolute value of that, and we want to view it on the interval from 2 to 6. So we look at that. Now, when we see the absolute value of f double prime on the interval from 0 to 6, we can see that it's decreasing. We see that the maximum value of the absolute value of f double prime on the interval is the absolute value of f double prime at x equals 2. So at x equals 2, the second derivative is -1/4. So the maximum of the absolute value of that is +1/4. That's that factor that we're going to use in our error maximum formula. That's the upper bound that we have on the error using this approximation. So now we can substitute all of those values, the 6 for b, 2 for a, 4 for n, and then the 1/4 for the maximum value of this absolute value of the second derivative. And we get a maximum error of this 0.083 repeating. So we know that our area, or our area approximation, is within 1/12, plus or minus 1/12 of a unit of the actual area under that curve. So if we want to, we can use Desmos to calculate the value of the integral, give us a decimal approximation out to 1, 2, 3, 4, 5, 6, 7, 8, 9, 11 decimal places. And so we get that. If we look at the difference between our approximation using the trapezoid rule and the value of the integral using the Desmos numerical calculator, then we get this value of 0.027. So the maximum value of our error was at 0.083. And the actual error is much less than that. It's 0.027 approximately. Now we're going to do pretty much the same thing with Simpson's rule, except rather than using these line segments here and approximating the area under the curve with trapezoids, we're going to use second degree polynomials on sort of double intervals. So rather than looking at the interval from 2 to 3, we're going to look at the interval from 2 to 4, and then we're going to look at the interval from 4 to 6. And then we're going to use those 3 points on that interval to infer the coefficients of a second degree polynomial that best fits through those points, or that actually fit through those points. So we can do that. Let's do that now. And when we use Simpson's rule, again, we're using that second degree polynomial to approximate the function on the interval of interest. And we're using those first 3 points. Now, we could set up a system of 3 equations and 3 unknowns and find the coefficients a, b, and c of that polynomial ax squared plus bx plus c ourselves. We could do that on paper using sort of pre-calculus techniques for solving systems of 3 equations with 3 unknowns. But it's easier and faster if we let Desmos do the work for us. So what we'll do is we'll create a table of values. We'll say I want my XY pairs on the graph of f of x. So I list x equals 2, 3, and 4. And I have the function, or Desmos approximate the function values there. So it's natural log of 2, natural log of 3, and natural log of 4 are given by those values. So we've got those values there. And we want a polynomial that fits through those 3 points. And we can get a polynomial that fits through those 3 points if we evaluate ax squared plus bx plus c at x equals 2, 3, and 4, and set the corresponding y values to natural log of 2, natural log of 3, and natural log of 4. That gives us 3 equations with 3 unknowns, and those unknowns are a, b, and c. So you can solve for a, b, and c doing that. We're going to have Desmos do that for us. Using their regression capabilities, excuse me, we get f of x has these coefficients, a, b, and c. They're listed here in this cell. But they're automatically sort of saved for us. So if we just type A, B, and C, we see the A, B, and C values that were calculated by Desmos with that regression calculator using the points in our table. So my first polynomial that's going to approximate this function has these coefficients. So I just type P equals AX squared plus BX plus C. And I write P sub 1 because I'm talking about that polynomial on that first sort of double interval from 2 to 4. And I want to graph that on the interval from 2 to 4. So we graph that and we see, look, it's almost indistinguishable from the graph of natural log of x on the interval of interest. You can see there is a little bit of a difference. If you get really close, if you zoom in a lot, you can see a tiny difference, but it's a very, very small difference between that polynomial and the y values on the natural log of x graph. Now we're going to approximate the area under natural log of x on the interval from 2 to 4 by this area under that polynomial instead. We can see that they're very, very similar. We're going to do the same thing using the points 4 natural log of 4, 5 natural log of 5, and 6 natural log of 6. So we plot those points again, and then we create a table of values, and then we have Desmos come up with the coefficients for that second degree polynomial that passes through those points. I can't use a, b, and c again because those have already been used for the last polynomial. So I called these a sub 1, b sub 1, and c sub 1. And then I typed in p sub 2, that's my second polynomial, is a sub 1 times x squared plus b sub 1 times x plus c sub 1. And I'm interested in graphing that on the interval from x equals 4 to x equals 6. So we graph that, and that's what we see. And then we want the area between that curve and the x-axis on the interval from 4 to 6. So we get that right there. And we see that that area between under those 2 polynomial functions on the intervals from 2 to 4 and then 4 to 6 is very similar, very close to the actual area under the natural log graph. Now, we came up with a theorem. We derived a theorem just through algebraic manipulation that said that the integral from a to b of a second degree polynomial is actually, I think it was, what was it? Was it b minus a divided by 6? I'm not sure. I don't remember what that coefficient was, but I remember that for the sort of bulk of it that depended on the polynomial, we had the polynomial at a plus a polynomial at B plus 4 times a polynomial at the midpoint. So we're going to use that to approximate this function, or approximate natural log of x on each interval. So it was b minus a over 6. I was correct about that. So we're going to have b minus a over 6 out front, and then we would evaluate the function at 2 and at 4, add those together, and add 4 times the function at 3. And that's going to give us the exact area under that polynomial function on the interval from 2 to 4. And then you do the same thing, and you end up using f of 4 again. So you have f of 4 plus 4 times f of 5 plus f of 6 times that b minus a divided by 6. And that's going to give us the area under this function. So when you add those together, there are some y values that are counted twice. This y value in the middle at x equals 4, that natural log of 4, is counted for the first polynomial and the second polynomial. And then because of the nature of the formula, at the midpoint of each of those subintervals, which is all of the x values with odd subscripts, so this is x sub 1 and x sub 3, those are always multiplied by 4. So what we get for the Simpson's rule is f at the first point plus 4 times f at the second point plus 2 times f at the third point plus 4 times f at the one after that, and then just f at the last point once. So the coefficients at the beginning and at the end are 1 because we only include those function values at the beginning and the end once. But then we see this 4, 2, 4, 2, 4, 2 pattern for the middle terms. The x values with subscripts that are odd have a coefficient of 4, and x values with coefficients or subscripts that are even have a coefficient of 2 if they're in the middle and 1 if they're at the end. And n always has to be even whenever you're using Simpson's rule. So if we do that, or if we use that formula to approximate this area, this is what we get. That b minus a divided by 6 becomes that b minus a, we end up with b minus a divided by 4. That's the delta x divided by 3 times all of these values over here. So this is that b minus a, which is actually on every interval, it's going to be 2 times delta x divided by 6. And 2 times delta x divided by 6 is actually just delta x divided by 3. So we're going to take our delta x, which is that b minus a divided by the number of subintervals, which is 4 in this case, and we're going to divide it by 3 or multiply by 1/3, same thing. So we take that, that's our coefficient, and then we have that 1, 4, 2, 4, 2, 4, 2, 4, 2 pattern. The second last one is 4 times the function value, and then we've got the very last one is just one of those function values. So we do that for Simpson's rule, and we get an approximation of the area under the curve of 5.363. Now, every time we use a numerical method, again, there's an error in the approximation, and we always have a maximum bound for that error. That will allow us, and that maximum bound will shrink as the number of subintervals goes to infinity. We can make that error as small as we want if we take the number of subintervals as large as necessary. So we might need n to be larger to get a better approximation, but we can make that error smaller and smaller and smaller by taking the number of subintervals larger and larger and larger. So this is our error formula. It's b minus a to the 5th. This is the error formula for the maximum error using Simpson's rule. B minus a to the 5th divided by 12 times the number of subintervals to the 4th times the maximum of the absolute value of the 4th derivative of the function. So we need to compute the 4th derivative. We've already computed the 1st and 2nd derivative when we use the trapezoidal rule. So the 3rd derivative is the derivative of negative x to the negative 2, which gives us negative 1 times negative 2, which is positive 2, times x to the negative 3, or 2 divided by x cubed is the 3rd derivative. And then when we take the derivative of that again, we're going to have 2 times the derivative of x to the negative 3, which is negative 3 times x to the negative 3 minus 1. Negative 3 minus 1 is 4, so we end up with a negative 6 divided by x to the 4. Now, we want not just that function value, but the absolute value of that function. We want the absolute value to be at a maximum on the interval from 2 to 6. So we graph the absolute value of the fourth derivative on the interval from 2 to 6, and we can see it. We can see just from looking at it that this function is decreasing and the maximum value occurs at x equals 2. So when we plug in 2, we get -6 divided by 2 to the fourth, which is 16, or -3/8, and we take the absolute value and we get +3/8. So that's 3/8 times that b minus a to the fifth, which is 6 minus 2 to the fifth, divided by 12 times 4 to the fourth, gives us our maximum error. So when we substitute those values into our formula, we get a maximum error of 0.125. So it's not bad. It's just an eighth, right? And then we say, okay, well, what is the exact error? What's the difference between the integral and that approximation using Simpson's rule? It's the exact error is actually much smaller than that. The exact error is 0.001, so 1,000. We're within 1,000th of the true value of the area under the curve. So we see that Simpson's rule is giving us a very good approximation, much, much better than even what we were expecting using that upper bound of the error formula. So it's pretty good. These are excellent approximations. And of course, if we wanted our error to be smaller, we could always take more subintervals. Now, there's one constraint with Simpson's rule. With Simpson's rule, the number of subintervals has to be even so that we can use that formula. And it's not just so that we can use that formula, but so that we can pair those subintervals like 2 at a time from x sub I minus 2 to x sub I. And then the next 2 subintervals, and the next 2 subintervals, and the next 2 subintervals. When we do that, we get 3 points, and those 3 points will determine the coefficients a, b, and c of that second degree polynomial that we're using to approximate the integrand in each case.